Welcome to FAR Module 4, Section 1. This presentation provides an introduction to phosphorus nutrition of ruminants. My name is Phil Garnsworthy, and I am Professor of Dairy Science at the University of Nottingham School of Biosciences. Phosphorus has important implications for the environment. Phosphorus enters watercourses through runoff from land, from leaching from soils, and from soil erosion. When it enters watercourses, phosphorus causes eutrophication, which is also known as algal bloom, which can kill plants and kill fish by taking the oxygen out of the water. Phosphorus comes from fertilizer applied to the land and from animal manure, either applied to the land or from the natural defecation of animals. In a survey performed in 2016, the sources of phosphorus applied to UK soils came from both manure sources and non-manure sources. Dairy manure accounted for 19% of total phosphorus applied, beef manure 16%, sheep manure 9%, pigs manure 4%, and poultry manure 9%. The largest single source was fertilizer applied to crops and grassland. There was also some phosphorus applied through sewage sludge from human sewage treatment, and there was 3% of other sources of phosphorus. So in total, ruminant systems account for more than 50% of phosphorus applied to UK soils. A survey was published in 2004 which looked at the annual phosphorus inputs and outputs on typical dairy farms in the UK. There were 86 dairy farms in total, and data reported per farm or per cow per year. The inputs of phosphorus consisted of fertilizer and feed. Fertilizer on average accounted for 977 kilograms of phosphorus and feed 1,763 kilograms. So the total phosphorus input into the average dairy farm was 2,740 kilograms. Outputs of phosphorus consisted of milk, livestock and manure that left the farm. Milk accounted for 1,044 kilograms per farm. The net livestock output, which is the difference between livestock brought onto the farm and livestock leaving the farm, accounted for 68 kilograms. And manure export, which was manure that was probably sold to an arable enterprise or another farm, accounted for 444 kilograms per farm. So in total, the inputs into the farm on average were 2,740 kilograms, and the output was 1,556, giving a net surplus phosphorus of 1,184. There was a tremendous range in all of the inputs and outputs, and some farms even had negative surpluses, which meant that more phosphorus was being exported out of the farm than was actually being brought in fertilizer and feed. In terms of per cow, the total inputs of phosphorus were 21 kilograms per cow per year. The total output was 12 kilograms per cow per year, and the total surplus was 8 kilograms per cow per year. So at the time this survey was conducted, then feed was a significant proportion of phosphorus input, and it contributed a significant proportion to the surplus phosphorus being produced on dairy farms. Now we will look at the role of phosphorus in ruminant bodies. Phosphorus has more known functions in the body than any other element, and 80 to 85% of phosphorus is found in bones, where with calcium it acts as a structural component. Cell membranes, genes, enzymes, and nutrient transport all involve phosphorus. Phosphorus is also involved in energy metabolism, and it's very important in rumen microbial synthesis. And of course, one of the main functions we're interested in is that phosphorus is secreted in milk. We will now look at the flow of phosphorus through dairy cows. Starting with the phosphorus in the feed, then some of that will be unavailable to the animal and will be excreted in the feces. The rest of the phosphorus is available phosphorus. Some of that will be absorbed by the animal, some will be absorbed by the microbes in the gut, and some will be unabsorbed and will be excreted in the feces. Some of the phosphorus taken up by microbes will not be available to the animal because the microbes themselves might be excreted in the feces. This is particularly true for microbes that are generated in the hindgut. However, when microbes are digested by the animal, then the phosphorus they contain can be absorbed by the animal itself. Once phosphorus has been absorbed, it's available for the tissues and the milk, and a very small proportion is excreted in the urine. Phosphorus excreted in the milk represents an irreversible loss of phosphorus to the animal's body, whereas phosphorus taken up by tissues could be later mobilized to support milk production, or may be mobilized to move around from one tissue type to another. Another destination for absorbed phosphorus is that it might be recycled via the saliva and become available in the gut either for microbial uptake or to be reabsorbed by the animal. This is a very important feature of phosphorus metabolism in ruminants. Because of the rapid growth of microorganisms in the rumen, then the phosphorus requirements of rumen microbes are very high and maybe even higher than those of the host animal itself. Saliva is the main phosphorus source for rumen microbes, and saliva provides a rapidly available source of phosphorus for the microbes, whereas availability of feed phosphorus depends on the rate at which the microbes can break down the feed. The salivary glands concentrate phosphorus compared with plasma by up to 16 times the concentration. And phosphorus flow via saliva is typically between 50 and 75% of phosphorus intake. Because ruminants have evolved this recycling mechanism, then when they're fed on very low phosphorus diets, phosphorus can be conserved by recycling, and ruminants can actually survive for a considerable length of time with very low phosphorus levels in the diet. The next slide shows the distribution of phosphorus in the tissues of a typical dairy cow weighing 600 kilograms. 3.8 kilograms of phosphorus is found in the skeleton, 500 grams in the soft tissues, 100 grams in the gut contents, and 70 grams in the plasma and extracellular fluids. The phosphorus in plasma and extracellular fluids can be rapidly exchanged, and up to 90% of this available phosphorus can be mobilized in a 10-day period and can be replenished in a 10-day period. Phosphorus in the skeleton is slowly depleted and replenished, and up to 30% of stored phosphorus in the skeleton can be mobilized or replenished over a period of about 3 months. If the animal is given phosphorus that exceeds its requirements, then the extra phosphorus is excreted in the feces. This review shows that over a wide range of phosphorus intakes, there's a very strong relationship between phosphorus intake and fecal phosphorus excretion, and roughly 2/3 of phosphorus that was consumed was excreted directly in feces. When we look at the requirements for phosphorus, it's very important to take into account phosphorus availability. Some phosphorus found in plants is bound into the cell structure. For example, phytic acid is bound within cell walls. This is a problem for nutrition of non-ruminants because they lack the enzymes necessary to break down phytic acid and release the phosphorus. Whereas in ruminants it's not an issue because the microbes in the rumen have phytase available to break down phytic acid. Availability values in the older literature range from 0.5 to 0.7, but these are underestimates because they don't allow for recycling of phosphorus via the saliva or excretion of excess phosphorus via feces, so the apparent availability is not really the same as true availability. Recent studies have shown that the true availability of phosphorus is between 0.8 and 0.9 for low phosphorus diets. So the current recommendation is to use an availability value of 0.75 for all feeds. This table shows the most recently published equations for calculating phosphorus requirements of ruminants. The equations were taken from NRC 2001, which in turn was based on AFRC 1991. Requirements for maintenance are expressed on a grams per kilogram dry matter intake basis, and for milk yield, grams per kilogram of milk. For growth, it's grams per kilogram of gain, and for pregnancy, grams per day. Requirements for maintenance are estimated from the dry matter intake of animals, the saliva flow, saliva phosphorus concentration, and the rate at which phosphorus is reabsorbed that was originally secreted in saliva. Requirements for pregnancy are based on the rate of growth of the conceptus, which increases exponentially as pregnancy progresses. Requirements for growth are based on the expected mature weight of the animal and its current body weight. The coefficient for mature weight is positive because animals which will attain a larger skeletal size require more phosphorus per kilo of live weight gain. The exponent for body weight is negative, however, because as animals get heavier, then they're laying down a smaller proportion of lean tissue compared with fat, and therefore the phosphorus content per kilo of live weight gain will be getting smaller. Requirements for milk production are based simply on the phosphorus content of milk. The main difference between these new recommendations and previous versions is that an availability value of 75% is assumed across the board. This is based on the rate of loss of endogenous phosphorus rather than having different availability values for each individual feed. When the equations are used to calculate the phosphorus requirements for dairy cows over a range of milk yield values, we see that from 15 kilograms per day to 55 kilograms per day, the phosphorus requirement increases from 40 grams of phosphorus per day to 97, which is equivalent to 2.5 grams per kilogram dry matter, increasing to 3.2 grams per kilogram dry matter. Values shown here are for total phosphorus in the diet rather than looking at available phosphorus, as the same value is used for availability across the board. These current recommendations are now 30% lower than they were in 1991 and should reduce phosphorus excretion to the environment. Phosphorus requirements for growing beef cattle and sheep depend on the live weight of the animal and its live weight gain. In these tables, some examples have been shown, and dietary phosphate concentrations range from 2.0 to 3.3 grams per kilogram dry matter for beef, from 1.8 to 2.9 grams per kilogram dry matter for sheep. Again, these values are on a total phosphate basis, in which requirements have already been adjusted for availability. Historically, phosphorus has often been overfed to dairy cattle. As seen previously, the requirements are 2.5 to 3.2 grams of phosphorus per kilogram of diet dry matter. Some surveys conducted in the 2000s found much higher levels than this. In the US, a survey published in 2003 found an average concentration of 4.4 to 4.5. In Northern Ireland, a survey published in 2009 found an average concentration of 4.8, and in 2016, a survey conducted in England found an average concentration of 4.2. Now, the reason behind this higher concentration in practice is twofold. One is that it's hard to generate low phosphorus diets, but there's also a mistaken belief that higher phosphate aids fertility, and there's no modern evidence for this. The idea that high phosphorus is necessary for fertility dates back to studies in the 1930s and 50s, when it was found that phosphorus supplements improve fertility. But when looking in more detail at those studies, the control diets were severely deficient in phosphorus. More recent studies, for example the ones published by Satter in 2003, found that feeding phosphorus in excess of requirements had no benefit for reproduction. This was supported by a study in Northern Ireland, published in 2009 by Ferris, where there was no difference in reproduction when comparing 4.5 with 3.6 grams of phosphorus per kilogram dry matter over a period of 4 lactations. In the study of Ferris et al. 2009, they compared 100 dairy cows fed typical phosphorus concentrations, which were 4.5 grams per kilogram dry matter at that time, with cows fed on a lower phosphorus content diet that was designed to meet requirements at 3.6 grams per kilogram dry matter. They fed these cows continuously for the first 4 lactations on either the high or the low phosphorus diet. They measured dry matter intake during the winter feeding period and found no effect on dry matter intake for any of the lactations. They measured milk yield throughout the whole lactation and found no effective phosphorus level on milk yield. So the conclusion is that phosphorus concentration of the diet can be reduced to 3.6 grams per kilogram dry matter without affecting performance. Based on what we've learnt so far, we can now look at target phosphorus levels for different types of animals. These values are all in grams of phosphorus per kilogram of dry matter. If the concentration of phosphorus is above 3.7 grams per kilogram, then surplus phosphate is being provided, and that will just be excreted in the feces. A value of 3.5 to 3.7 is considered adequate for high-yielding dairy cows. That's cows yielding more than 8,000 kilograms of milk per year, and also for young beef bulls. A target level of between 3 and 3.5 is adequate for low to moderate yielding cows, and also for growing beef and sheep. The Dutch target for dairy cows with low to moderate milk yields is between 2.5 and 2.9 grams per kilogram dry matter, but this could be marginal under some UK situations, as we'll see in the next slide. Below a concentration of 2.5 grams of phosphorus per kilogram dry matter, then there's a clear risk of phosphorus deficiency. This slide shows the total phosphorus content of some feeds in grams per kilogram dry matter. The forage values were obtained from a large UK analytical feed lab, and we can see that grazed grass has an average value of 2.7, grass silage 3.2, maize silage 2.1, and whole crop silage 2.7. So if fed as a sole feed, the only forage that would be adequate would be grass silage fed to beef cattle. Cereals contain slightly more phosphorus than forages, and the averages for barley are 4 and for wheat 3.5. Sugar beet pulp has a low phosphorus content of 0.8. Cereal byproducts have a much higher phosphorus content. Wheat feed, for example, 10.9, maize gluten feed 10.0. And protein supplements tend to have high phosphorus contents as well. Soya 8.5, rape meal 12, distillers grains 9 from wheat and 8 from maize. Beans have a phosphorus content of 9. Sugar beet molasses have a value of 1, and dicalcium phosphate, which is used as a mineral supplement, 180. As mentioned, the values given for forages are averages taken from an analytical lab. The amount of phosphorus in a forage depends upon soil phosphorus content and the amount of phosphorus that's applied in artificial fertilizer or manure. And the range in analytical values for forages can be very large. For example, grazed grass varied from 1.7 to 6.6, grass silage 0.6 to 5.9, maize silage 0.3 to 3.1, and whole crop silage 1.9 to 3.7. So it's very important when trying to ration accurately to have the forage analysed for phosphate content. Otherwise you can be underfeeding or overfeeding phosphorus. Note that protein sources and cereal co-products have high phosphorus concentrations. As a result of this, in typical balanced diets, it can be difficult to formulate low phosphorus diets, that is, diets that exactly meet the requirements. There are a few points to consider when formulating diets with phosphorus requirements included in the formulation. Firstly, diets formulated to meet energy and protein requirements using typical ingredients will usually contain adequate phosphorus to meet requirements. Therefore, inorganic phosphorus supplied in mineral supplements is only needed when the basal forage has a low phosphorus value, and that should be checked by forage analysis in the lab. Another point is that any effective constraint costs money. So because phosphorus is quite high in protein supplements and to a lesser extent in cereals, low phosphorus diets will generally be more expensive. And sometimes it will also be impossible to formulate diets without excess phosphorus, but the excess can be lowered by reducing the phosphorus content of the diet. This table shows some example formulations to meet the requirements for a 40-litre cow. Both diets meet the metabolizable energy and metabolizable protein requirements. Diet A is based on grass silage plus cereals and traditional protein supplements, including soya and rapeseed meal, and some bypass fat. Diet B is based on grass and maize silage in equal proportions, with mainly byproducts as the supplementary feeds, including sugar beet pulp, citrus pulp, palm kernel, distiller's grains from wheat and rapeseed meal, again with some bypass fat. You can see that both diets provide the same amount of metabolizable energy, and both will meet the metabolizable protein requirements. The phosphorus content of both diets exceeds phosphorus requirements, which is 3.0 to 3.5. So to summarize what has been said in this presentation, firstly, phosphorus requirements of cattle and sheep are much lower than typical feeding practice. Phosphorus supply at 3 grams per kilogram of diet dry matter is adequate for most ruminants. It could be increased to 3.5 grams per kilogram dry matter for high-yielding cows and young beef bulls. Feeding excess phosphorus has no fertility benefit and just adds to pollution risks. However, formulating low phosphorus diets can be challenging. Typical least cost formulations that meet energy and protein requirements will usually contain more than enough phosphorus, unless the forage component of the diet has a particularly low phosphorus content. Similarly, there's generally no need for inorganic phosphate supplement unless laboratory analysis of the forage shows a very low phosphorus content.